Join us on Tomorrow's World Today as we journey through the worlds of inspiration, creation, innovation, and production to find the ideas and technologies that are shaping our future. On this episode, we visit the world of production to explore how ductile iron pipes are made and how constantly innovating something that has been around for millennia can make a huge difference in our infrastructure. Did you know that we didn't have running water in the U.S. until the 1800s? Let's join our host, George Davison.
Our ancestors would carry a pail to a water source, and they would fill it with water and then carry it back to their homes. Can you imagine doing that in today's world? I surely can't, and I don't want to. Thank goodness for human ingenuity, because it led to the invention of the pipe. This invention helped create grids and systems to carry liquid to and from our homes. Even before big machinery was invented to install the pipe, we used animals, like this elephant, to help lift the pipe and then lower it down into the ground. And while piping has been around for almost 200 years, this type of pipe, it's evolved. Do you know the difference between these two pipes? This is gray steel pipe, and this is ductile pipe. Ductile pipe is stronger, lighter, more durable, and even more cost-effective than its predecessor. It's also made from over 90% recycled material, like these old car parts right here. While piping and infrastructure are used every day, you probably don't think about it at all until one day they stop working. Look at the size of that pipe. I'm sending David to Alabama to show you the latest in innovation in how piping's made.
I'm at the main mill of U.S. Pipe's headquarters in Bessemer, Alabama. And I'm surrounded by scrap metal, but none of this metal is going to waste. You see, the steel industry has been recycling steel scrap for more than 150 years. Today, U.S. Pipe is turning this scrap into ductile iron. In the 1950s, ductile iron pipe became the better alternative to cast iron. It's stronger, more durable, and it just simply lasts longer. Different linings and coatings have been created to prevent corrosion and add to its longer life. I'm meeting with Jeff Mason to learn the chemistry behind how this is turned into the ductile iron our underground infrastructure depends on.
Hey, David.
Jeff, good to meet you.
Good to meet you. Welcome to Bessemer, Alabama.
Thank you. What's the weather like up there?
Hot and humid, just like down here.
Yeah. So I've been standing here for a while, and I've been noticing a specific chemistry that's been going on over here. Could you tell me about that process?
Yeah, so what we got going on here is we got really two general piles that we're picking from, and that crane operator is mixing those in different ratios, and somewhat similar like making a cocktail, right? The cocktail we make here is iron. And so today what we're making is ductile iron, and we've been making iron pipe here since 1899.
I didn't realize so much went into making ductile iron. Could you tell me about that process?
Yeah, so what we're making, right, is ductile iron here. It starts off as gray iron when we initially melt it. And gray iron, we're probably familiar with like an old cast iron bathtub, right? Big and heavy and thick. Ductile iron came about in really the mid-50s, where we do additional treatments downstream in this plant so it can be a thinner profile and it can take impact without fracturing and breaking. There's a cupola inside, and that's where we melt that iron down into a molten metal, and then this feeds two plants on site that make ductile iron pipe. And so I'm gonna walk you through the cupola, take a look, and then we're gonna go somewhere where it's not quite so hot and loud, and we're gonna talk about what we saw.
Great.
All right, let's check it out.
Yep. The process of melting down iron starts at the top of this cupola where scrap metal is loaded. Cupolas have actually been around since the 7th century. They are still used today as a means to melt iron because of their low cost and simplicity. Whew. Way cooler in here. What is it, 2 million degrees out there?
It's extremely hot out there, isn't it?
Yeah.
We actually keep track of it on this monitor up here, and right now we're at 2,872 degrees Fahrenheit.
That's hot. So when we were out there, I noticed a lot of things. And one thing I noticed, there were 2 troughs. Could you tell me what each trough is for?
Yeah, so you got the 2 troughs. The main trough is what conveys the iron, and then we have a diversion trough, which it conveys all the slag away from the iron. So that allows us to maintain the iron in its purest form. On top of that, right, we're standing in the control room here, and this control room, in almost real time within a 5-minute window, monitors what's in that iron that's pouring into these ladles and allows us to make adjustments as needed.
All right.
So we still have gray iron, and after this, we're gonna go check out when we convert that into ductile iron by adding magnesium, and then we're gonna go watch the pipe get cast.
Let's do it.
Let's check it out.
US Pipe has been repurposing steel scrap for over 120 years. Instead of this scrap ending up in a landfill, they repurpose it and turn it into ductile iron piping. So far, we've learned some of the chemistry behind the melting process. Now it's time for the pouring stage.
Okay, David, so this is where the magic happens, right? We're gonna take gray iron and we're gonna turn it into ductile iron. So we have a 10-ton ladle here, and we're gonna pour in magnesium. So sitting on the bottom of that ladle is magnesium. And so you can see all this white flash and heat, right? That's a reaction happening with the magnesium, which is changing the gray iron. And what it's doing is it's changing the graphite. So you got graphite in it in the form of a flake, and it's changing that flake into like a nodule or a glass ball. So now with ductile iron, it's much stronger, much more durable. And so with that, let's go watch pipe be made.
Next, the metal is transported by a ladle or a series of ladles to the back of a casting machine, where it's poured into troughs so that it can be spun in the mold and cooled by water, which is being sprayed onto the mold.
And so we're gonna keep spinning that until that pipe cools down enough so that it actually shrinks and can be pulled from the mold.
Wow, man, you weren't kidding. This radiant heat is a lot.
I know, right? It still is maintaining temperature. So right now what we're seeing here is the other side of the pipe end, which we call the bell end. And so this is a sand core which acts as a plug, which goes in the end. It stops the iron from coming out the end, but it also is where our bell shape comes from. And now this arm is gonna go in, expand, and it's gonna pull this 16-inch pipe right out. And you'll see on the end, that's the bell where the spigot inserts into. So here comes the pipe. And in 3 minutes, you went from molten iron to a full stick of ductile iron pipe.
It's impressive.
So now we've got ductile iron, but it's got one more heat treatment to make it even more robust and durable, and that's called annealing. And so let's go check that out.
All right.
Okay, so we just took the recently cast pipe, and now we're gonna lift it and bring it over here into the annealing oven.
So these pipes were already molten. They were all extremely hot. Why are you heating it back up?
So we're doing a secondary heat treatment because it's gonna make it even more strong and more durable. We bring it back up to 1750 degrees and then bring it down to 1350. It all takes about an hour, and at the end of it, it's a much more strong, durable, even more ductile pipe. But let me show you the real heat's at. All right, like I said, this is where the real heat's at. Let's take a look inside this oven.
Hokey smokey, you're not lying, that's hot.
Yeah, so it's about 1750 degrees in there. That pipe is white hot, as we like to call it. And so You'll cook a marshmallow in about 1.5 seconds.
I believe it.
So after about an hour of this, we're done annealing it, and then we can quench the pipe, get it down to handling temperature, where we can start to do secondary processes like quality control. So moving from the hot side to the cold side.
All right. It's hot.
This is the end of the annealing oven. So it's still 1,300 degrees here, and we're leaving the hot side and move to the cold side of the plant. And so what's gonna happen is this pipe's gonna leave the annealing oven, and it's gonna roll over into a roller, and that roller is gonna make sure there's no ovality in it. It's nice and round for future installation. And then immediately after that, we're gonna cool it down in the sprayer. And that's gonna get it down to handling temperatures, so that way we can start to begin our QC process. So now we're cooling the pipe down to handling temperatures.
Is this just water, or do you have some magic elixir?
No magic as far as I'm aware of. Just recycled water. So everything we do here is on a closed loop, so we don't waste any. And so after this, we start performing our QC. Okay, so now we're officially in the quality control part of the manufacturing process.
So what exactly are you looking for in quality control, and what happens to the product that doesn't come to that standard?
We're making sure that the pipe itself can hold pressure, and then we're going to test the material properties of the iron itself. And anything that fails goes back out to the scrap pile, gets broken up and remelted in the cupola. So this is the first step. It's a hydrostatic pressure test. We take it to 500 PSI. It's all or nothing. If that pipe is ductile, it'll pass. But if it's not ductile, it'll fracture, and out to the scrapyard it goes. After that, we then start testing the iron itself, making sure it meets the standards we say it does, and then it goes to cement lining. So we're gonna go check out cement lining. Let's go. So all this pipe passed quality control. Now, once we're done with that, we bring it over here to cement lining.
Cement, why do you use cement?
Cement actually has two benefits. One, it's a corrosion barrier from the iron and the water. But second, it can help balance water chemistry in harsh water environments.
That completely makes sense to me. So are there other materials you can use besides cement?
There are. So we got a epoxy lining is one, and a glass lining amongst several others, but those are the main two. And those are, more like for wastewater environments or sludge. But let's go walk over there and see a little bit closer.
Yeah.
It's a little loud here, but you can see that there's a lance. And there's actually two of them. We do two at a time. And those lances go inside the pipe that's spinning. And that lance injects cement, slurry, into the pipe. And it gives it a nice equal thickness throughout the entire length of the pipe. The target is anywhere from 1/16 to 1/8 of an inch thick. We have a clear angle here of the pipe rotating, and that lance is injecting cement while that pipe is spinning, and we get that even thickness.
So what's happening here? I see a lot of water.
Yeah, it might look like we're washing the cement out of it, but what we're really doing is cleaning that bell cavity. The gasket fits into that bell cavity, and that has to be cleaned because that gasket has to hold pressures up to 350 PSI.
I see the pipes entering the oven. What is that for?
This is what we call a curing tunnel. And so what it is it's high temperature, high humidity. And that allows the cement to dry without cracking. And the whole process only takes about an hour, which normally would take much longer. High humidity keeps that cement from drying out because then it cracks. So this humidity keeps the moisture within the cement. Okay, so we got done with our lining process, and right after that, we're on to our coating process.
So I assume just like the interior has different linings, that the exterior will have different coatings depending on the purpose of the pipe?
Yeah, so what's occurring right now is our standard shop coat. But outside of that, for additional corrosion protection, if you want it to be, 150 plus year service life, what we can do is add a zinc coating. On top of that, we have multiple other specialized coatings for specialized applications. But after this, we're kind of at the end. We're going to bundle it and we're going to ship it, and it's off to its end user. So follow me and we'll go see it. All right, we're at the end of the line here, right? So now we're at bundling and packaging.
One of the things I've enjoyed most at my time here is just seeing the growth that I've seen. The automation in this mill is way different than what I saw in the last.
Yeah, so this mini mill here is a much newer mill, right? So with that, we're able to take advantage of a lot of the new current technologies. And those technologies like this arm where it picks it up and turns it, right? That makes it more efficient and safer. And so that's really important to us. And so that's it. And now we're off to shipping, and then it gets to go to its final home.
Sounds great.
All right. This is the yard. This is where all the finished product comes until we ship it to its final destination. Ductile iron pipe has always been a material of choice because of its durability and long life. We think that municipalities and owners are starting to especially realize that the word resilience and reliability mean more now as we start to see higher density living and know that it costs a lot to put a pipe in the ground. We anticipate that the ductile iron market will continue to grow as people realize that the materials that they choose do have an impact on service life.
Jeff, I've had such an insightful trip. I've seen engine blocks being melted down, becoming finished pipe, and everything in between. I know Vic's meeting George in Pittsburgh, and that's where I'm headed.
Well, we love being a part of this industry, and we hope you've enjoyed it.
Hey, Vic.
How are you, George?
Welcome to Invention Land.
Absolutely. Thank you for having me.
You bet. Well, we've been waiting for US Pipe for quite a while to get here. We've been wanting to tell this story, and you guys have been at it for quite a while. Long time, a lot of innovation over the years. I hear there's quite a few innovators down there working on things.
There are. It looks very simple. Our pipe carries water from point A to point B. Where we spend our time innovating is on making sure that that pipe will do that no matter what's happening around it. So around innovation, right, we're thinking about population change, population growth, climate change, and all the stresses that's going to put on water infrastructure, and how do we do our part? So take deep freezes, for example, right? Our pipe now has a solution to make sure the water's not going to freeze. Wildfires is another example. I've actually watched our pipe burn in a fire for over 20 minutes.
Yes.
And not only does the material stand up to it, but the water inside the pipe actually insulates the gasket, and our pipe functioned beautifully, and not all materials can say that.
Very nice.
And then finally, just thinking about earthquakes and earth movements, and making sure that our pipe has the ability to deflect and flex a little bit while still maintaining all of that strength.
Well done. So what's the next big move? Where are you heading in this technology world with pipe?
Well, this piece of pipe right here in the joint that I brought you is actually our latest HDSS.
Okay.
And what you see is we have a typical gasket structure, but we also have a weld bead, and then we've got these locking segments. And they go in just one slot, and you just kind of slide them down, so they're incredibly easy to install. And then ultimately, when pressurized, creates an enormous amount of resistance.
Interesting. So in other words, I'm sliding this pipe in. You're going to bring two pipes together, and then you put your rubber gasket in there, and it can still move a little. But with this mechanism here, this blue mechanism which you jam in there, it basically takes up all the tolerance. So you have a very resilient and reliable come-together spot.
Incredibly resilient pipe that could sustain those kinds of earth movements and anything else that came its way. Because at US Pipe, we're not just thinking about how do we create a product for the next several decades, we're thinking about centuries. And we have plenty of pipe that's been in the ground for over 100 years, And we're thinking about how do you create pipe that could last 200 years,
Yes.
maybe even longer than that.
Right.
Because the need for water is not going to go away, and it will always remain essential, and that's what we innovate for. That's our job.
They've gotten stronger, lighter, more resilient. You know, this is looking like it might fit around here. It looks
Well,
like
it's kind of
all-
heavy. I'm not sure I want to take it back with me. I would love it if you could find a home for it here.
You know I have a home for it. I'm putting it
Excellent.
right in there where the museum is, and we got all those kids coming through here. We'll tell a good story on this one too, Vic.
I appreciate it. Thank you so much.
Thank you, Vic. Oh, yeah. Got one down.
To learn more about the content in today's episode, visit us online at www.tomorrowsworldtoday.com.